Hey guys, how are you? Welcome back to Introduction to Computer Networks. Oops. Hey, that's up. Okay, sorry guys. Interesting. Okay, give me a few seconds. Having trouble muting. Sorry guys, I'm having trouble stopping the audios. Oh, this is horrible. Okay, give me one more second. There. All right, finally. Hey guys, sorry for that. Sorry for the glitches. I just updated the version of my Stream Deck. I guess the newer version of Stream Deck is not exactly compatible with my old settings. Okay, sorry. I will still need to restart Stream Deck. So if you would allow me a couple seconds. Okay, so while it's starting, let's talk about week 11. Yeah, and did I finish the greeting? Okay, welcome back to Introduction to Computer Networks. This is Polly again, streaming live from NTU, National Taiwan University here. Okay, you know what? This is week 11. All right, and how are you guys doing towards the end of the semester? The audio is echoing. I'm actually not quite sure. Okay, are there other students hearing echo? Oh, okay. Okay, so maybe Eslam, see if you can wear a headphone. Okay. Okay. Good. Good. Glad that we get the version issue resolved, at least for today. I'm gonna look closer into that. It's a little bit odd. So when I was practicing earlier today, everything is fine. And okay, until we started streaming, then things problems show up. Okay, so this is week 11. Good thing is that we'll be talking about a new chapter which does not concern exam 2, so no worry. We are not in a hurry to try to finish any chapters. And the load this week, okay, is light. You see, only 2 quizzes doing, and these 2 are straightforward, and we'll finish them in class, okay? And the reason that the load this week is light is because exam 2 is tomorrow, okay? Guys, I understand towards the end of the semester, things can be getting out of control a little bit. Guys, don't overthink it. Just hang in there. Do whatever assignments comes up, and all you need to do is to do the best you can. There's nothing more you need to do, all right? And after 5 more weeks, summer is ahead, okay? And so you can relax totally then, okay? So think that way, all right? And make sure you do take a rest, a good rest, because you see that you have lots of stuff, here crowded in the brain. Having a good rest and do something else will get those things out of the head so that you have a clear mind to learn new things next semester. Okay, good. Just hanging there. Okay, good to know that there's no echo. So Eslam, try wearing a headphone. That might help. And so exam 2 is coming up tomorrow. Okay, but no worry. You've experienced exam 1 already, right? And so you see that it's going to be happening Wednesday in the morning, 10:20 to 12:10. And you know that before the exam starts, Polly needs to do the ID check. This is required for the online exam. So I still need to make sure you are who you are. So if you are able to come earlier, please do. Okay, that would allow Polly to start the ID checking earlier. And we might be able to start the exam earlier and therefore finishing the exam earlier. The scope for the exam is now certain. Okay, it's going to cover PA 3 to 7. And in terms of the technical content, that's going to cover chapter 2.6 to the end of chapter 3. All right. And all the rest will be the same as detailed in exam 1. Okay, so definitely revisit exam 1. Okay, that should help you recall how the process is like. So the Google Meet you need to join tomorrow and the exam form for tomorrow are both ready. Okay, so make sure that your camera is also working. Hopefully it's not going to be like Polly earlier today. So have your camera working, taking the headshot from shoulder up. So there are going to be problem sets in the exam, just like exam 1 that is related to the PA assignments. Okay, so for your convenience, the firewall is off. Okay, so you don't need to do an AT. You can just directly connect to the PA workstation tomorrow. Actually, it's already off now, so you can do that also. Okay, today. Now, exam accounts. So you guys know that you have an exam account. The username is exactly your student ID. And I've changed the passwords of these exams account after the first exam. Okay, so I'm now telling you what the password is. Okay, so all of you are reset to use the same password. So guys, log into your account and change the password immediately to avoid other people being able to log into your account, all right? And make sure that you write down the new password somewhere so that you don't forget. And to ensure a smooth run tomorrow, so definitely go through the exam 1 channel or the course website, the exam page again. Okay. So you know that the duration is 90 minutes, and during the exam, we'll try to stay quiet. You would post your questions on the Google Meet session, the chat box. And you want to come back and check whether there are people asking questions you want to ask as well, and what the answers are. Okay. And what's a little bit new for exam 2 is this. Okay, for exam 2, the PA related problems, some of these might require you to write a server. So you need to program a server. For a server process, you'll be running on a certain port, and you know by now that that port needs to be unique. Okay, so your server process needs to run on a unique port number, and other students' server process will run on their own unique port number, so that you guys' port number will not conflict, so you can debug, okay, your server process. So for this purpose, each of you is assigned a unique port number that you can use, okay, for those exam problems. So if you click into this link, you will see that, yeah, it's a table, okay, and the port number assigned to you, you can see, you find your student ID, okay, and look right. This is the port number assigned to you, okay. So I think in Ryan's case, your port number is 30103. All right. So bullet number 3 here is just something a little bit extra to what you have not yet experienced in exam 1. All right. Good. Now we're back to the lecture. So these are the topics today. So what you're seeing here is we are starting a new chapter. Okay, literally a new chapter. This is chapter 4. In fact, chapter 4 and 5, the two of them together talks about the network layer of TCP/IP. Okay, so previously the transport layer, right? And previously the application layer. Okay, so in this video, it's going to come into 3 parts. The first part, very brief, you will hear Polly talking about the goal. Okay, essentially what I want to teach you. Okay, yeah, what are the key topics? Okay, you would need to learn. And then the second part, slightly long, Polly will talk about the function, okay, what the network layer will do. Essentially, the transport layer takes messages from applications and wrap them into segments. Okay, so we call these packets in the transport layer segments. When these segments come down to the network layer, they'll be wrapped around by adding the network layer header. Okay, and we call a packet then a datagram. So transforming segments to datagrams from the sender side. At the receiver side, transforming from a datagram back to the segments. That's the main purpose of the network layer. And then you will see, however, in the animation of how a datagram will go through the internet. Okay, what you see distinctively here in the network layer is previously in transport layer, you see packets going hypothetically, conceptually through a channel end to end directly, okay, from sender to receiver. But in the network layer, okay, we'll be dealing with hosts. Okay, so you will see these datagrams traversing through many more devices through the internet and reaching the receiving host. And these devices in the middle, how we call them? The routers. Yeah. And finally, Polly will introduce the 2 major functions that's running in the network layer. And chapter 4 actually is designed specifically to talk about one of them. And chapter 5 talks about the second of them. All right, are you ready? Yeah, this is the first video, 5.5 minutes, a little bit long. Welcome to chapter 4, the network layer, and particularly the data plane. So in this chapter, the goals are understanding the principles behind these network layer protocols, and we'll focus on data plane and talk about the other one, the control plane, in chapter 5. So in the overview section, we're going to talk about the service models possible for these network layer services, and we'll talk about the main functionalities that people implement in the network layer, forwarding and routing. We'll talk more about these. And we'll be spending some time here talking about the architecture of a router and how packets travel through a router. And the rest of the chapter will be spending a lot more time here talking about forwarding of packets generally, as well as how it's implemented, how it's working on the internet. 4.1, the overview of network layer. Well, what the network layer is doing is simply this: transport segments from the sending host to the receiving host. So let's use the micro internet here as an example. And let's assume this guy here is the sending host, and this guy here is the receiving host. So the goal of the network layer service is so that we could send segments or packets through the internet to the receiving host. Now, what's a bit special though, in the network layer? It's not only the two end hosts have the network layer protocol implemented and operating on the machine. Each and every router inside the network here would also have the network layer protocols running. Now, to be exact, on the sending side, on the sending host here, the transport layer segments is going to be encapsulated into the datagrams. So a packet at the transport layer is called the segment. But when a packet now goes into the network layer, it's called a datagram, and sometimes also called the IP datagram. So transport layer, TCP layer. Network layer, IP layer. Transport layer, we have the TCP segments. Network layer, we have the IP datagrams. So at the sending side, we encapsulate these transport layer segments into the IP datagrams. Now these grams, datagrams, will go on to the network and travel from router to router. And each of the router will examine something special, in the packet header, in the IP datagram header, and decide where to pass it further on. So that magic we'll talk about more in the sections to come. Finally, when the packet arrives at the receiving side, so this is the receiving host, the network layer is going to look at the datagram, remove the packet header, and pass the segment up to the transport layer. So that is the lifetime of a packet traveling the network through the network layer. So in animate, so packet coming from above, pending the header, so packet gets a bit bigger, and you see routers busy forwarding the packet and eventually reaching the receiving host. And at the network layer header or the IP datagram header removed, and the segment restored and pushed up to the higher layer. Alright, so that is the general picture of what the network layer protocol is doing. Now, the network layer protocol is doing two major functionalities. As you observed earlier, yes, forwarding. The routers are all busy moving packets around from one router to another router. Hopefully, it gets to the next router that is appropriate, so we don't take too much time to pass the packets until it reaches the receiving host. The other is this, this is also the magic that I was talking about. So this is the computation, the intelligence in the network layer that determines a route between a pair of sending host and the receiving host. Or a lot of times we just call them the source and the destinations. So to determine an end-to-end path to travel over the internet from the source to the destination. And that intelligence is also called the routing algorithms. An analogy is this. Let's assume the class is taking a trip to canteen. Yeah, I know the weather is getting warm. It would be really nice if we're in canteen. Well, the thing you need to do first is this, routing. You pre-compute or you Google, and come up with a plan, for the day of travel. Whether we take a bus to the Taipei station or we take a metro to the Taipei station. And from the Taipei station, do we take the high-speed rail? And from the high-speed rail station at Kaohsiung, do we take another bus, or do we all rent a car or rent a number of these bikes so that we ride along all the way to canteen? So the computation process, the intelligence that we need to do ahead of the travel is called the routing. Now, on the day of travel, we'll bring this Google map printout saying, hey, you start from home, you walk to a particular station, and you hop on a particular metro line. And once you get to the Taipei station, you just hop onto, high-speed rail number 112. And then after arriving at Kaohsiung, you go to a particular bus stop, and then you hop on the next vehicle taking you to canteen. So that is this forwarding. So at every interchange point, you look up a piece of paper and find out what is the next step to do. So this way, it ensures that the forwarding part, the traveling part is going to be fast and smooth. So the separation or the differentiation between the routing function and the forwarding function. So you see, forwarding running on the data plane, routing on the control plane, because the routing part is the one that requires intelligence, right? You need to figure out exactly which segment, what vehicle you take, etc. So forwarding is something that you have a printout, and on the day of travel, you just follow whatever the printout says. Okay. So in this next video, you will see Polly talking a little bit more how forwarding, routing is done on the internet, and you will see there are actually two suites of solutions. Okay. Traditionally, there's one that is actually trying to come up with routes in a more distributed way. Each router computes for the routes what they think is the optimum. But modern days, we actually take a more centralized approach, okay, to compute routes and then install the forwarding table. So two suites of solution, older time, modern time. One is distributed, the other more centralized. Okay, so pay attention to this video, very important, because Polly is gonna take a poll after the video and asking you another question. Okay, so this video. And that should make it a bit clear for you to see the separation between data plane and the control plane. So by data plane, we actually meant to talk about the forwarding function. Okay? And the control plane, on the other hand, is the routing function, the part that is trying to identify a path between the source and the destination. Now let's talk a bit more about the data plane. Okay, so what's being done there is very local. Each router is determining for each incoming datagram who should be the next router to forward it further. Okay, and that is the forwarding function. So it's illustrated here. For a datagram coming in, this router here is looking up a table and find out, oh, this should be the outgoing port, and therefore reaching the next router. Now, the control plane, on the other hand, is the part implementing the routing functionality, okay, implementing the intelligence. It is to determine, okay, how would the packets be able to travel end-to-end from the source to the destination. So these routing algorithms will be implemented in the control plane. Now there are two different approaches implementing the control plane. One is the traditional approach. The other is called the SDN approach. Okay? The traditional one is the distributed approach. And the modern one, the SDN one, is actually more centralized. Okay? To your surprise, isn't it? Okay, we are actually moving from distributed solution to centralized solution. Now in the traditional one, each router will be implementing the routing algorithm, and the routers will also exchange information among themselves. As a result, and collaboratively, they calculate an end-to-end path. Now, in this centralized approach, in the SDN, we actually ask a couple very powerful machines, okay, a couple very powerful SDN servers that are actually sitting far away from the routers to do the computation. And then after the computation is done, they're gonna install the routes back into the routers. Okay? So the tables are actually computed on the routers locally in the traditional way. But more recently, the modern way is to have some powerful machines computing all the routes and then install them back to the local routers. And local routers no longer do the complex route computation. So let's talk a bit more about the data plane. So this is the forwarding part. So this is the part implementing the per router action. Okay? And it's very simple, very fast. Okay? All that is done is the packet coming in. The router look at the specific packet header field and match to an entry in the forwarding table. Okay? So this is called the fast output interface lookup. Okay? Once we get a match, we get also the outgoing interface. Okay? Let me illustrate. So these are the routers. Okay? And inside the router, okay, you see this is the entire operating system stack. Okay? There's this thing called the forwarding table, and each router will have one of these. Okay? When there's a packet coming in like this, it's going to look into a packet header field, okay, and matching the pattern here to the entries in the table. Now, we see that this guy is the matching entry. Therefore, immediately we see the packet should go out on interface 2. Okay, so output interface 2. So this is the direction to forward the packet further, and therefore next is going to arrive here in this router. Okay, so this is exactly the detailed step of packet forwarding in the data plane. And the control plane is here, okay, higher up in the operating system stack. To be more exact, okay, and let's talk about the traditional approach first, where the computation is distributed. Okay, so the routing algorithm is going to be running on each of these routers, okay, and up here. Okay, the routing algorithm here, 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 and here. Okay. So each and every router, okay, is going to have the routing algorithms running, and they're going to interact with each other. So there are these exchanges of messages, okay, between these routing algorithms distributed on the routers. Okay. And this is the control plane. As a result of the computation and exchange, okay, they find out what should be the forwarding table, okay, for different incoming packet, for different packets going to different destinations, and install the local forwarding table into the data plane. So this is the separation of the control and the data plane. Now, in the modern days, we take the centralized approach, the SDN approach. Now, it looks a little bit different, the separation of the data and control plane. So routers protocol stack, okay, stop right here, because the computation is all where? Up here, okay? A couple machines, powerful machines, okay, doing the computation. But it cannot be computing without information provided by the routers here. So these routers, okay, will have a tiny little process running here. They're called the control agent. The control agent here is gonna provide input to the remote controller. This is the big process, implementing the routing algorithm. So after collecting information about, hey, who they are and the connectivity of these routers to other neighboring routers, now this controller here can then do the powerful computation. Once the result is obtained, okay, those tables are communicated back, sent back to the control agent, and therefore installed into the data plane of the routers. All right, so the poll is there. So if you think about it, right, the distributed approach is a little bit more like democracy. Each router can compute and decide on their own what is the best way to other destinations. But in the centralized approach, hey, there's a central computer, powerful computer there computing the routes. Okay. All right. Interesting. Are you guys seeing the result? Okay, so you guys are voting. Very interesting. Okay, it's not yet done, I guess. So I'm actually not quite sure how to show. Okay, you guys are changing. All right. Very interesting. Okay, so let me end poll now. Okay. So you see that, hey, wait, I actually can see the result from here. Yeah, but towards the end, what we see is that it's some 50-something%, okay, choosing the centralized solution. And then the other 40-something, okay. Until today, okay, the traditional way of doing routing versus the SDN, software design networking way of routing, some people like one versus another. So actually, it reflects pretty well, okay, what the reality is. Okay, but guys, that is also saying that democratic systems versus tyrannic systems, okay, there could be good and bad in either way. All right. So again, the message is still that in a system design, there are very often trade-offs. It really depends on what you are designing for. Okay, so your users. So I guess in the routing case, imagine this: if the routes are messed up, who will be influenced? Chances very high that a whole bunch of users will be influenced, a whole bunch of destinations will be influenced. Is that good or bad? Not good, right? So if you give freedom to individual router too much, it's very easy for one router to mess up the internet. Okay, and now you can imagine why the internet routing is a little bit more tyrannical these days. All right, so let's move on to the next topic. Okay, the service models. If you recall, in the transport layer, we also talk about service models, right? To establish a connection, to send messages from one end to another end, there's a connection-oriented way to do it, or a connectionless way of doing it, which corresponds to UDP and TCP. In the network layer, how you establish a path, okay, from one end to another end, there are also okay, connectionless and connection-oriented way. So in this first video, you will see that the internet is more connectionless. And there are some legacy networking technologies that are doing it the connection-oriented. And you will also feel that the connection-oriented network layer is pretty much circuit switching. Before we talk about the service models implemented at the network layer, let me remind you this. If you recall, when we were talking about RDT, we say sending process, receiving process. If the underlying channel is reliable, all they need to do is just to pass data out and the data is just going to arrive. But unfortunately, the channel is not exactly reliable. Okay? And depending on how unreliable the channel is, the complexity of the reliable data transfer service is going to be different. More unreliable, more complex. Less unreliable, less complex. Okay. So the service model we'll be talking about next is to talk about how we implement. Okay. What kind of channel we're providing here? Are we going to provide a more reliable channel or less reliable channel? So more reliable channel is one service model. Less reliable channel is one service model as well. And we could actually have a spectrum of different service models here. There are two major camps of service models. First is the connectionless service. What it meant there is that the end hosts and the routers in the middle, they do not set up any connection-specific states before data being passed around. So there's no reservation of bandwidth, no reservation of memory space to buffer packets. Okay, so you see that there's not going to be any guarantee at all. Exactly. So this connectionless service is also called the best effort model. Okay, and this is exactly the model implemented in TCP/IP, the internet. The second camp, the connection-oriented service, which is the opposite. So the end systems, as well as the routers in the middle, they would actually exchange message and establish a connection before the data flows. Okay. So this is actually implemented in some of the old architectures, old systems. ATM, this is not the bank ATM machine, banking machine that you withdraw money. So this is actually a specific computer network that have been designed in the 20th century. At some point, okay, ATM is actually competing with the internet. I think towards late 90s, okay, still before the turn of 21st century, ATM gets merged into the internet. So some of these routers in the internet, the lower architecture design is actually from ATM. Now, frame relay X25, these are just too old, okay, but these are examples of connection-oriented network layer service. Okay. Now, to establish such a connection will involve routers, okay, and the involvement is actually quite deep. It's complicated enough. It's the third important function, okay, in these systems, on top of routing and forwarding. Okay. Now, one last bit I want to talk about is this. We've heard about connection-oriented service as well when we were talking about TCP, right? TCP, they're sending SYN ACK, and then ACK for the SYN ACK. Hey, that's the establishing connection, right? It sounded very much like these, ATM frame relay X25 is doing. Yes. At the transport layer, TCP is actually establishing connection between two processes. At the network layer, in ATM frame relay X25, they are actually also establishing connections between two hosts. All right? But be careful. Internet at the network layer does not implement connection-oriented service. However, at the transport layer, implements connection-oriented service. So just be clear. Internet, the subject we're talking about and we'll continue to talk about, does implement connection-oriented service at the transport layer, but not at the network layer. Internet, in fact, when it is designed, it does have this complexity at the edge mindset so that we don't do complex things in the network layer involving the routers. All right, so that's the general idea. So when you talk about designing a network generally, there are, again, two flavors of service models. And internet is the connectionless one. And so for the rest of the lectures today, as well as the rest of the semester, we'll focus on talking about this connectionless service model, the internet model. And so the next video talks about the router on the internet, the architecture. So in there, you will see components, and you will see also which component implements what function. Now let's take a look into the inside of a router. this is the general architecture. We do have a processor, which is doing the routing algorithm. So the complex route computation is being done here. The processor is quite high-end, very much comparable to the CPU, high-end CPUs we're using these days, except that the processor here might be a bit more optimized for route computation. Second most important entity, the switching fabric. Well, people will argue this is probably the most important entity because this is the part of the router that is doing the actual switching, the actual moving of the packets. Okay? And we know that the packet needs to be moved very, very fast. So these switching fabrics definitely needs to be high speed. Third, the input and output ports. Okay? By output ports, input ports, I actually meant that these network interface cards, okay, that we use to connect to the routers that are passing data in, passing packets in, as well as connecting to routers, okay, that we pass the packets out. Okay. Now, you see then, yeah, the lower part is where the packets are flowing through. So this is the data plane, meaning this is the part of the router that we are flowing the data. So the functionality there, very important, just to move packets. In order to be very, very fast, yeah, the computation, the switching there is pretty much hardware optimized. And so they can work in this time scale, the nano time scale. On the other hand, the upper plane, that is the control plane. Now we have the routing algorithm implemented as software running there. So in addition to routing, it does also a little bit of the management of the router. Okay? For example, tracking, monitoring, how many packets coming in, how many packets going out, things like that. Okay. Now, this part being implemented in software then operates in a slower time scale, the millisecond time scale. Now, the one most important functionality for the router to do is forwarding. Now, it also does route computation here. Okay. Now, connection between the route computation and the forwarding here is this. After the route is computed, we install the forwarding table into the memory of the incoming network interface here. Let's zoom in a little bit more into the input network interface so that we see a little bit more the forwarding functionality. Where does it happen? And it's happening right here. Okay, the component that's connecting the input network interface to the switching fabric. Okay. So what's being done there is essentially switching, and it's done in a decentralized way, meaning for each of these input port, each of these input network interface, there's a lookup processor. Okay. So the forwarding of packets coming into each of these input ports is done parallel across all these input ports. So that's what they meant here, decentralized. So each lookup processor here is doing this. It looks into the header fields in the packet, okay, and it's seeking the output port using a forwarding table that's installed from the route processor, and that is installed already into the input port memory here, okay, right here. So the goal here for the incoming network interface is so that it can complete, okay, the input port processing, the lookup forwarding, okay, at the line speed, okay, meaning, hey, if this is the speed of packets coming in, now this forwarding process needs to be fast enough so that we get the same output speed here. Okay. If this is slow and this is fast, so if this is R prime and R prime is smaller than R, then we'll end up having this. Okay. Packet gets queued. Packets need to wait somewhere in a temporary buffer before they can go out. So that's queuing. Datagrams, if they arrive faster than going out into the switch fabric, then there's queuing delay. Now, there are two different kinds of forwarding. In the traditional internet, we do the destination-based forwarding, which is to look at the packet header fields, particularly the destination IP address, and only the destination IP address. Now, in SDN, the modern routing, it's called the generalized forwarding because we can actually look at multiple header field values, not just one. And it can be arbitrary combination of these header fields. Okay. So it's a lot more general. But you can also see that provided the same lookup processor, okay, this is going to be a bit faster and this is going to be a bit slower. So in order to keep up the speed, okay, if the incoming is R and output is R prime here, in order to make sure this R prime is as high as possible, usually in SDN, okay, these SDN routers will need a faster lookup processor here. So this one here, SDN routers, more expensive,
while this one here, usually more affordable.
Okay, next we'll look into the forwarding function more, finding out exactly how forwarding is done. So what it's done is by basically taking the destination address in the packet and matching the table entries. And so one can do exact matching. Table entry is also a bunch of potential destination addresses, okay? And you do exact match. The problem is that, hey, how many destinations there can be? Probably many and too many, right? So that forwarding table there can be very memory consuming. So in order to make this table a little bit more concise, okay, because when the table is shorter, matching can also be faster because the possibility is lower. Okay, so instead of doing exact match, on the internet, forwarding is done by doing the longest prefix match.
So that was the router architecture. Now, there's one thing I want to talk about which is very, very relevant to the rest of the chapter. Okay, destination-based forwarding. Okay, as you heard, forwarding is based on, for each packet coming in, look at the packet header field and try to match an entry in the forwarding table. Okay, so if the destination address says this, 11001000, matching this guy here, then we take this output port, okay, output link interface. If it matches, for example, this IP address, okay, then we take output port 2. What happened inside this forwarding table is, if you think about it, right, there are so many possible destinations on the internet. And for each destination, there needs to be an entry, isn't it? So this particular destination's output interface being 0. So in fact, okay, in a forwarding table, you should be seeing for each possible IP address, what is the output link interface? For each of these IP addresses, what is the output link interface? But the thing is this. Okay, how many possible destinations there can be? Well, the IP address is this big. Okay, the IP address, 8 bits, 8 bits, 8 bits, 8 bits together, 32 bits. So you could have actually 1 gig entries. Okay, and each entry might require, you see, 4 bits. 4 8 bits. That means at least 4 bytes, and maybe another byte here for the link interface. So each entry here at least needs to be 5 bytes. So 5 gig, 5 bytes, and that would be 5 gigabyte at least, just to keep the forwarding table. Okay, so the input port network card there, okay, it's gonna require not just a high-speed lookup processor, but also a lot of memory space. In addition to the buffer space might be required, right, in case queuing occur. So that particular interface there is already very costly. And if you need to have many input ports, many output ports, think about the cost of a very high-end router, very expensive. And that's not going to scale very well if we actually, expand the IP address space. So this is a 32 bits IP address. This is IP version 4. Later on, you'll see. Okay, there's another version of the IP layer protocol. That's called the IP version 6. And the address space there is actually expanded to 28. So this approach, each IP, each entry, is not going to scale very well. So what's really being done on the internet is this. We do matching, all right, but not match the entire IP address. We only match the prefix, okay, of the IP address. So we're doing table lookup is to do matching, but we are only matching to the longest prefix. Okay. So this is what we do when we're looking up in the forwarding table entry. So given the destination address, okay, so we'll take this address and match the entries here. Okay. This time we don't have 1 entry per IP address. It's actually an aggregated or the prefix. So what you're seeing here is we only specify the first part of the IP address and leave the rest general. Okay. So that is also saying that as long as the destination address, the first few bytes match this pattern, okay, the rest of the IP address can be general, free. Okay. Now, as long as you have a destination IP address looking like this, then we take this packet to this output port. And the second entry is saying that, okay, if the IP address matches this pattern, the rest can be flexible. No matter what, we go to output port 1. Now, there could be multiple entries. For example, this guy here and this guy here, you see here. Oh, up to this point, they are the same. So you could have an IP address matching both entries, isn't it? So in this case, we'll take the longest prefix. Okay, we'll take the entry that the destination IP address matches the longest. Okay, now, in case the rest of the 3-bit of this IP address is 000, then we forward that packet to output 1. If it's something like 101, then it does not quite match this entry. However, matching this entry, then we send it to output 2. All right. So let's exercise a little bit. Now, if we get a packet, the destination address is this. What should be the output interface? Let's see. The first 8 bits match. Great. In fact, all these 3 entries, the first 16 bits, actually 19, 20, yeah, the first 20 bits are all the same. So these two destination address, I think the first 20 bits are also the same. So what differs is beginning from the 21st bits. So which entry in the forwarding table does the first destination address match? Well, this is 0. So only this entry match, right? Because this is 1, this is 1. So these two not matching. Therefore, this packet goes to interface 0. Now, the second destination here. 21st bit is 1. So it should be either one of these. Now, 000. Well, it actually matches more the second entry. Therefore, the outgoing interface for the second destination address being 1. And that takes us
to the quiz. Okay, so this is quiz 33. Okay, so hey, again, we have a forwarding table here, and we have 4 packets with different destination addresses. Okay, so find out what interface should this packet go. What interface should this, and this packet go? Let's go to the discourse space. Okay. Guys, you guys are given 3 minutes time, so let's all work this out. Okay, so all of you within 3 minutes finishing the quiz will all get bonus. Okay, so let's start. Yeah, I guess this is too easy. Yeah. Good. So 0312. Just match to the longest prefix of the entries, okay, in the table. Very good. So hey, guys, let's then move on to the next quiz. Okay, 34. Now, how about we know that all these IP addresses should go out to link interface 0? Can you somehow write the whole set of IP addresses into a prefix so that you have a prefix-based forwarding table? Okay, so let's go to quiz, to the discourse space, channel W11, quiz 34. Okay, similarly, you have only 1 minute left. We have only 1 minute left to the end of the class. Sorry for the glitches about the Stream Deck. Otherwise, we would have enough time to finish the quiz. But I guess it's not that hard, right? So why don't we work on this and see, okay, whether you guys manage to answer quiz 34 as well, okay? So 3 minutes as well. Okay, so Polly will be borrowing 2 minutes of your time. Okay. Okay. You need to type up the pattern. Yeah, it takes some time. Very good. Yeah. Sorry that the alignments are all messed up, Zhixiang. I know you're a temp. Okay. If the characters are all the same size, then your table will look great. Yeah, I guess it's quite clear, right? So you can see from the slide. For the first prefix, it should match all the way to the 28 bits. So 3 8 bits and 4 more bits, right? For the second entry, it should match to the 18th bits. There we go. And for the third entry, it matches, 24 bits. Okay, yeah, straightforward. Okay, and that's what the routers are doing, generating the forwarding table. Good. And with this set, guys, I think you guys have get the idea. Okay. And you can see that quiz 33 and 34. Yeah, there you go. I think Team A has mastered Discord. Okay, very clear. Zixuan, good job. All right, great. There you go. Obvious. Okay, well done. And so, with that said, I see you tomorrow morning for the exam. Right? Try to take things easy. Okay, it might be easier than you've expected. And hope my audio will not mess me up this time. Okay, working. Great. See you tomorrow. Bye, guys. Very interesting. Bye.